Welcome everyone. So this is our 18th live stream geometry. So it's right about 10 a.m. and we have 4 people with us already. So we have a new person today, Ansuman, and then we have a few recurring people. So Anmal comes almost every week, and then also Ram and Irajan are both recurring people on my channel. So thanks everyone for participating. So today we're going through problems from the Ukrainian Correspondence Olympiad. So it's a contest. Originally the problems were in a magazine, and I believe people would mail in their solutions to that contest in the magazine in Ukraine. But then I think the magazine went away in 2016, but they still continue the contest. So that is what we're going to be doing today. So I'm going to share my screen. All right. Okay, so here's the first problem. All right, let me maximize. So the diagonals of the cyclic quadrilateral intersect at point E. I feel like I've had a couple of these cyclic quad problems before where, or pretty recently on my channel. So let me draw a cyclic quad. A, B, C, D. And a lot of the questions I did recently, the diagonals are perpendicular, but here they don't have to be perpendicular. So the diagonals intersect at E. Let P and Q be the circumcenters of BCE and DCE. Interesting. All right, so I'm going to draw those circumcircles. That's one circumcircle, whoops, BCE and DCE, the centers. So center of P and center of E. We're calling them P and Q. So that should be P, and this should be Q. That's interesting. All right. A line passing through point P parallel to AB. So maybe it would have been better to, let me think about this. You know what, I'd rather draw it like this. So, or actually I could just move the points around. So what if I go like this? There we go. All right. Hey, Enrique, thanks for joining.
Hey, Michael.
And yeah, thanks for posting the link on that forum for Mexico.
Sure, yeah, thanks for letting me do that.
Yeah, it's awesome. So we're on our first problem. All right, so P and Q are the circumcenters of BCE and DCE. And a line passing through point P parallel to AB. Okay, so let me draw AB and AD. So we draw that parallel line, and we draw this parallel line through Q parallel to AB. Looks like GeoGebra helped us out a little bit. So it looks like they intersect on AC. I'm not sure why yet, but I wouldn't think it would be that hard to prove. So let's see if we can do it. Oh, that's the problem. Prove that R lies on AC. Okay. So what we found using GeoGebra is exactly what we have to prove. Now it might be easier to let one of the parallels meet AC at point R prime and then show. Yeah, there's a couple different ways we can attack this. So yeah, I mean, we could let R, we could define R like that, or we could let PR meet AC at R prime and then show that QR prime is parallel to AB. That might be easier.
If we can show that C is the center of homothety from PQR to Wait, that doesn't make much sense. Okay. Sorry.
Oh, you're saying we could like try to find a homotopy? So it looks like BP and CQ meet on the circle. So I wonder if that's relevant to the problem. I'm guessing that should just be an angle chase. So
Yeah.
all right.
In that
Okay, so yeah, maybe it's the radical axis theorem also. Just trying to think.
try finding RP and then using sine law or something, because sine law also contains circumradius.
Okay. You say RP, try to find RP. FPQR is cyclic. Yeah, because the angles are parallel. Yeah, FPQR is cyclic. And it seems like it also passes through C, which is also just an angle chase. And then once we know that, yeah, it seems like there's enough information here where, let's see. Yeah, okay. So
we can go with our original idea to let it intersect at R dash and then prove this cyclic and then angle chase this.
Okay. Yeah. All right. So I think that should solve it. So I'm going to write it up. All right. So I'm going to delete this circle for now, and I'm going to call that R prime. And I think we can show, okay, yeah, we don't know that CQ and FP meet on the circle yet, but I'm going to prove it using an angle chase. So I'll write it out like this. Okay, so first I'm going to define R dash. So let the parallel through P to AB meet AC at R prime. All right. So first I'm going to show DQ and BP meet on the circle. I don't even know if we end up using that, but so I'm going to write it like this. So the angle between BP and CQ, or I should say BP and DQ, is 180 minus angle PBD minus angle QDB, which is equal to, let's think about how to rewrite this. So that's 90 minus angle PDB plus 90 minus angle QDB. And that should be equal to, start a new line here. half angle BPE plus half angle EQD, which is equal to angle BCE plus angle ECE. Wait, where am I going with this? Yeah, okay. Which is equal to angle BCD. So basically, this whole angle chase, whoa, that was all in one line. Let's hope I can separate it. Let's see what? How do I break it up? I go like that. I won't try this. Enrique, did you remember how to do this? How to break it up into separate lines? I could try this. Backslash, backslash. Hey, Rodrigo. Thanks for joining. So let's try backslash, backslash. See, does that? Ooh, it worked. I should have done that all along. So, all right. Yeah. So since the angle between BP and BQ is equal to angle BCD, that means BQ and BP and DQ intersect on this circle. So all right, so we can draw that intersection point, and we can call it F. Oh, BP and DQ. Did I write it differently originally? Sorry.
Yeah, it's CQ.
Oh yeah, you're right. BP and DQ. And then, so yeah, first, yeah, I wonder if we can show CF. So if we didn't define R prime, if we instead defined R as it is in the problem, the intersection of the parallels, then I see how we could prove that that is a cyclic quadrilateral. But yeah, we're working at it the other way. So let's see. Just thinking this through. Oh, you know what?
We see that CR dash P is equal to CAB is 180 minus BFC.
Yeah,
So
so
CFPR dash is cyclic.
Yeah, so CFPR dash is cyclic. That's kind of like Rhimes theorem. So you just proved it.
And
yeah,
here we are done now that if we let say S dash be the intersection of Q with parallel through Q with AC, then S dash also has to lie on the circumcircle of CFP. So basically S dash and R dash are the same points.
All right, so we have angle CR prime P is equal to angle CAB, which is 180 minus angle CFB, which is 180 minus angle CFP. And so that means that CFPR prime is cyclic. All right. And then if we do the same thing with Q, we would get that CFQ S prime is cyclic.
We need to prove that CFPQ is cyclic here. We are missing one more thing.
Oh, we still have to prove CFPQ is cyclic, you're saying?
Yeah. That is, I guess, possible by angle change because we know angle QCE and PCE.
We know QCE and BCE. Yeah, so that,
Yeah, we get that in terms of angle CDE and angle CBE and then take it to angle A. And we know that angle BFD is 180 minus A, so we are done.
okay. So I'm gonna show Q is also on that circle. So you said we know angle QCE, I think, right?
Yeah, QCE is 190 minus half of CQE because Q is the center of the circle and half of CQ is angle CDE.
Okay, so I'm just thinking through this. Okay, so we have angle QCE is it's 90 minus half of angle CQE, or yeah, which is 90 minus angle CDE. So yeah, I'll write it like this: angle QCR prime is QCE, which is 90 minus half of CQE, which is 90 minus CDE. We want to show that's the same as Q.
90 minus CDE is equal to 90 minus CAB.
Okay.
And CAB. That's CAB
Oh,
in the
I'm sorry, CAB.
Yeah, similarly, we see that angle PCE is 90 minus CAD.
And PCE.
By similar logic is 90 minus CAD.
Did you say PCE?
Yes.
Okay, so by the same logic, PCE is 90 minus
CAD.
D.
Now we add both of them to see that angle PCQ is 180 minus angle A. And we know that PFQ is 180 minus angle A.
All right, so adding them, PCQ is 180 minus angle A. Oh, and that's okay. So we add the two. So angle PCQ is 180 minus angle A, and
PFQ is also 180 minus A.
okay, and that's equal to PFQ.
So PFCQ is also cyclic, and so these 5 points lie on the circle.
Cyclic.
Now we can directly angle chase angle QR dash C.
All right. So
QR dash C is equal to QFC, which is equal to DFC, which is DAC, and we are done. DFC.
Oh, sorry, DFC, and that's equal to DAC.
And so QR dash is parallel to AD.
Let's see if this all fits on one line. There we go. All right, so I will draw that circle just for the fun of it. And we will move on to the next problem. Thanks for your help in that. All right. Let's see, let O be the circumcenter of triangle ABC. Hold on just a sec. So O is the circumcenter, N is the midpoint of arc ABC. So I usually end up drawing it this way. Right, that's N.
It said arc ABC means the arc AC containing the point B.
Oh, one sec. I think sorry.
If that's a confusing notation, they should have wrote arc AC with.
Oh, the midpoint of arc ABC. Yeah. So, yeah, that's weird. Yeah, I wonder, did they mean that? Midpoint of arc ABC. Yeah, okay, we want B at the top. Yeah, we want it like that. Okay. Thanks for joining, Akan. So we have a big group here now. It's awesome. So N is this point. All right. On sides A, B, and BC, mark D and E such that O lies on the segment DE. Whenever I see this, I think Pascal's theorem. So I have a hunch that we might end up using Pascal's, but let's see. Just because okay, so that's D, and that's E. And then BN and BC intersect at P. And EN and AB intersect at Q. So that's a little off the page right now. Let me shrink it a little bit. There we go. So this is point Q. And we want to show that PQ is perpendicular to AB. This problem looks really familiar. I feel like I've seen something like it before. I don't know if I've seen the exact thing before. But yeah, it looks familiar. Whoops. All right. It looks like the problem where I use the gliding principle. So I think the reflection of B, yeah, the reflection of B over DE lies on the circle. I think I did this in like video 99 on my channel. But yeah, if you reflect B over DE, it lies on the circle. I wonder if PQ and B prime are collinear. Ah, so close. But not quite. All right. All right. So if we so I'm going to do this. So it's often very useful to do this. So then by Pascal's theorem, CD and C prime D and A prime E meet on the circle. Yeah, I don't know if that helps us with this problem though. But that's like a common trick. We'll just draw it in anyways, why not? Try to prove PQ is parallel to NO. Yeah, that's a good idea. That will definitely solve the problem.
Barycentric does finish this off, I guess.
Barycentric makes it easy.
Yeah, but I guess we are not allowed to bash things here.
We're not allowed to bash things on my channel. Yeah. All right. PQ, let's see. Yeah, maybe we could show, just trying to wonder if we could like use an orthocenter somewhere. Let's see.
Is QP by any chance equal to AC dash?
Is PQ parallel to AC? So AC dash is parallel. AC A prime C prime is a rectangle, right?
No, I'm asking, is the measure of PQ equal to measure of AC dash? C prime.
It might be. It looks a little longer to me, but maybe that's just my eyes. So PQ A C dash. Yeah, PQ is a little longer. Yeah, this is tricky. So let's see. So you see where DN meets BC, and we see where EN meets AB.
D and cyclic, I guess. No, wait, never mind.
It's all right. Let me see if I can find some cyclic quads. So yeah, we have a lot of primes. So yeah, B, D, B prime. Yeah, I'm not sure what the right strategy is here. Could we use the radical axis theorem? Let's see.
Another way, but might be risky, that use Siva's theorem on triangle BDE in trigonometric form. that we assume P dash is a point such that QP dash is perpendicular to AC, and then prove that these three CVNs are concurrent. But we might need to angle chase many things there.
Okay, so you'd like use trig Cheva for that? I feel like there's got to be a way to solve this without trig Cheva.
Does QP bisect angle BQN?
That does what?
QP bisect angle BQN.
Let's see. No. But let's see. We have to use that N as the midpoint of arc ABC. I think that's kind of what I've been leaving out. Somehow we have to use that fact. So, yeah, I don't think BNBE is cyclic. I think I did that already, but I'll just check it one more time. See it. But yeah, how do we use that N as the midpoint of arc ABC? Yeah, okay, so yeah, we want to show NO as, let me try something here for a sec. Yeah. The midpoint of arc AC. Yes, I can label that. Let's draw that in. BG, DE, and PQ. This might be like a Pascal's. That does look true. All right. So I think that seems like a good strategy. Yeah, I feel like we should be able to use Pascal's theorem here. Let's see. So Q is AB. Like maybe I should extend NE to meet the circle again. So P. Yeah, like what if I did this? Like, so this looks a little messy, but let's give it a shot. So that's point I, and this is point J. So how can I use Pascal's here? So so A, B, and JN meet at Q. IN and BC meet at P. Is it AI and CJ is the other point? That's off the screen, but let's see. Just gonna check. I think, yeah, by Pascal's, AI and CJ are concurrent with P and Q. So, okay, I'm gonna take a look. So yeah, can we show AI and CJ? So if they meet at a point, it's collinear with P and Q. Can we show that line is parallel to NG? I don't know. C prime, H, and J are collinear. Yeah, I mean, yeah, with Pascal's, there's like an infinite number of things. So yeah, C prime, H, and J are collinear, and yeah, there's just so much structure.
Just one thing, how have you defined the point H?
H is the intersection of BG with DE.
I think I have proved that H is collinear with P and Q.
Oh yeah, how'd you do it?
Yeah, the basic idea is that if H is the foot of the bisector of angle DBE, so it is true that HD divided by HE is equal to BD over BE.
Okay.
But P, Q, and H are collinear if and only if SEVA is true for the triangle KDE. So you have this ratio HD divided by HE, mess around with it, and you use at the end the fact that BN is bisector of angle KBE.
I see how you're doing it. So yeah, so DH over HE is BD over BE by the angle bisector theorem. And then you can use Cheva and you can, yeah, kind of get to proving it. All right. So if we know P, Q, and H are collinear, can we use that to solve the problem? So then we'd want to show PH is parallel to GN, which is probably just projective geometry, I would guess. I wonder if we could just use projective geometry from the, let me delete a bunch of stuff I added. I'm going to get rid of all the primes. I think they're kind of cool, like A prime and C prime and point F, but they might lead to like a more complicated solution. Can we just use projective geometry to show that PQ is parallel to ON? So if you project P and Q through point B, you'd get A, or you could get DE, let's see. All right, I'm going to redraw some. Okay. So if we can show that, if we can show that PQ passes through H using Cheva, it feels like it should just be a matter of projective geometry. Let's see, because I'm getting a little confused here. So O is the midpoint of NG. And we want to show PH is parallel. So basically PN, PG, PO, and the point at infinity are in harmonic conjugation. So, let's see.
BNO at cyclic.
BNO, oh, BNOH, or I'm sorry. What points were you asking about?
Doesn't EV look like tangent to circle of BNQ?
BNQ?
They do look like tangents.
Let's see. Do they look tangent now? I don't think so, right?
No. No, sorry.
Let's see. Let's see how much I can, sorry. I feel like this problem has to have a nice solution using Pascal. My brain is just not figuring it out right now, but yeah. So yeah, if we like created PB over PQ, possibly. Well, let's see. So we have a harmonic conjugation, right? So BA, BG. So these four rays, BA, BG, BC, BN, are in harmonic conjugation, right? So if we take that harmonic bundle, BA, BG, BC, BN, and we project it onto GN, no, I'm sorry, we project it onto EQ, we get QNE but then we'd have to see where BG, yeah. So we get PB over BQ and show it's cos A over cos C. If you let PQ meet BN at a point, then PQ, that, and H are harmonic. Yes. Have you proven that, or that would be true if the problem was true? Ah, well, that would solve the problem, because if we know that those 4 points are harmonic, at least I thought I had it in my mind for a sec. Yeah, we don't even need to project B onto the circle. We could just project B onto the line.
If projecting from B to the circle gives us a nice alternative proof that CI-PH are collinear. If we remove the segment PH, then we already know that NCGA is harmonic, and so projecting we see that QIPH should be collinear.
Okay, so we know N, C, G, and A are harmonic, right?
Yeah, product of opposite sides is the same.
Yeah. So then how did you get that Q, P, and H are collinear?
We can define H dash to be the intersection of QP with DE, and
Okay.
then project this to the circle. We see that it goes to, because this is harmonic, it should go to a harmonic thing, and so I goes to N, Q goes to A, P goes to C, so H should go to G. So B and BH dash G are collinear. So we can arrive at the fact that QPH are collinear.
All right, so I'm gonna write this up. Hold on just a sec. Okay. So let me erase some of the stuff I added. Okay, so okay, I'm just gonna call that H for now. So NAGC is harmonic, and if we project through B, okay, so you want to let, sorry, you want to let PQ meet D at H dash, right?
Yeah.
Okay. I'll just call it F for now. Let me just make that a segment instead of a line. And then NAGC is harmonic. So if you project onto line QF,
We already know by complete correlators that if I is the intersection of BN and QP, then QIPF should be harmonic.
okay.
And because a harmonic maps to harmonic, so BFG should be collinear.
Okay, so these 4 points are harmonic, and also, okay, so all right. Let me move this to the right a little bit. Yeah, when I just see so much structure, it's just overwhelming for me. I don't even know where to start the proof, but you have figured it out. So QP intersects DE at F, intersect DE at F, and BN at H. And then since those three are concurrent, we know Q, H, P, and F are in harmonic conjugation. So we have Q, P, H, and E are in harmonic conjugation. And then also NAGC is harmonic. So there's a whole bunch of ways to see that, but I guess I'll just mention one way. So kind of like you said, NA times GC is equal to NC times GA. That implies that NGCA is harmonic. And then if we project those 4 points through B, then we have yeah, actually, let me rewrite a couple things here because I didn't write the okay, so Q, so really we want A, C, N, E. So I'll say, all right, I like this, A, C, N, G. There we go. So then if you take those 4 points A, C, N, and G and you project it through B onto line PQ, I'm sorry, QPH and BG intersect BE. So that means, or BG. So that means that this should be F, not E. Okay. So F, it is BG intersect DE. And once we know that, now we can try to show PQ is parallel to NG. All right.
Is OH parallel to BG?
Is OH parallel to BG? I'm not sure.
Is OH and 90?
Let me move the figure around. They look, I don't think they are parallel. Yeah, they intersect way up there. Yeah. But I feel like we're really close, right? It's probably just, so O is the midpoint of NG, right? So it feels like, let's see. So F, so if we project GON infinity through P onto BN, we'd get BN H, or we want to show it's H. Is BN parallel to DE? I don't think so. No. Yeah, but I think that proves it, because if BN intersects DE at a point, so it's going to be way out here. So I'll say it like this. Let X equal BN intersect BE. So I'll say not drawn. Then XD or BH, BNHX are in harmonic conjugation. And then we can project those through P onto the line GN. So, or wait, what was I doing?
Project through F instead.
Oh, I'm sorry, project through F onto GN. Yeah. So, and then we have G N, and then FH intersect GN, and O is in harmonic conjugation. But since O is the midpoint of GN, that means FH has to be parallel to GN. So and that means that PQ is perpendicular to AC. That solves it. Yep. Pure geometry. Yep. No bashing. So yeah, we were able to get through it. All right. So I'll move on to the next one. Whoops. All right. So we have a triangle ABC where AB is less than AC. On side BC, they always put B at the top. I have to get used to this. So I'm going to, let's do this. B should be the top point. AB should be less than AC. Okay, that's fine. We want to mark a point B so that AB is equal to AB. So we're going to want to use our circle tool. Let's make it look nicer. So this should be point B. Side AB, change, add a backslash here. That looks a little better. Okay, so hold on just a sec. So DE passes through the orthocenter. All right, so let's see where that is. I'm just going to draw the altitude. So yeah, GeoGebra has a way to draw the orthocenter, but you usually want to end up seeing the altitudes anyway. So it's usually best to construct it manually anyways. So the orthocenter, I will have it as H. Okay. Whoops. And we want DE to pass through that. So this should be point E. And we want to prove that the circumcenter of triangle ADE lies on AC. All right. This seems interesting. Let me delete some of the excess just so it doesn't look so messy. Yeah, I wish there was an altitude tool in GeoGebra. So yeah, we just need to remember that AD is equal to AB. So then let's draw the circumcenter, draw the circumcircle of ADE. There we go. And let's draw the center of it. Oops. It does indeed lie on AC. So how do we prove that? I'm going to delete it for now. I'm going to just draw this point for the heck of it.
Is BE equal to BD? Maybe, looks like.
I don't know. Phantom points. Yeah, I was kind of thinking that. So like, let's see. Let me draw the perpendicular bisector of DE. Ah, that looks like it lies on, it lies on, yeah, so I mean, basically, if we label this point, it's the midpoint of arc DE, right?
This is that HA bisects angle DAB.
Exactly.
Which is of true because the figure is symmetric about its altitude.
Exactly. So for that reason, since AB is equal to AD, AH is the angle bisector, and so K is the midpoint of arc DE. And Hakan is saying that AHDC is cyclic. And that's probably an angle chase, I'm guessing. Okay, so, all right, so we made some progress.
Yeah, that's true because angle HAD is half of BAD and we know HCD also.
Yeah, so yeah, HAD is equal to BAH, which is equal to BCH. So yeah, that proves it's cyclic. And all right, so we want to show the circumcenter lies on AC. How do we do that? So I mean, the circumcenter of ADE is also the circumcenter of KDE. So maybe that helps. Let me draw the circumcircle of ABC, just out of curiosity. All right. So I wonder, I wonder if BL is perpendicular to DE. No. Oh, no, because we know KL is perpendicular to DE. Let's see, how do we compute angles? So yeah, maybe we could draw the perpendicular from K to DE and let it be L. And then we want to show L is the circumcenter of AED. That's one way to do it. Whoops. I kind of like that. Let's see. Yeah, so we draw the perpendicular from K to DE and we let it meet AC at L, and then we want to show L is the circumcenter of ADE. So if we can calculate angle ALD and angle AED, that would do it.
I think we should label the point of intersection of KL and ED, because we then will have HFLX would be cyclic and might use that.
Okay, yeah, you're saying like, yeah, this would be a cyclic quadrilateral here. But let's say, what if I hide this circle? Like what if I guess my strategy is like, no, because I think it's the way I'm defining things. Like my figure made it look like we knew L lies on the circle, but like we don't know. Yeah, we don't know L lies on the circle. We have to prove it. So if I drop a perpendicular, but wait, how did I define? Yeah, you need K to define the circle. That's the thing. Yeah, so it's a little tricky. You need K to define the circle, but then you want to show that L is the center of the circle. And yeah, HJLF is cyclic, so maybe that helps. I wonder if EFLD is cyclic. No. We know LE is equal to LD, yes. So if we can show LK equals LA, I believe that is true. Well, let's see. So no, because L could be equidistant from E and D, and also equidistant from A and K, but not necessarily. Oh, okay, well, no, because we'd also have to know like LE is equal to LK. I think there's like one more step after that. But I kind of like the idea. So LK is equal to LA. That should just be an angle chase. And LE equals LD, we know that.
Obvious, because we know KAL as 90 minus C, and we know KLA as JLF, and that should be 180 minus DHF. We can use the cyclic HJLF.
So, okay.
We need that KLA by 2 plus KAL is equal to 90.
Yeah, no, I think we got it. I think we're good here. Because we know AEKD is cyclic. We just want to show L as the center of it. So yeah, if we can show L lies on two of the perpendicular bisectors of the circle, because we know the circle exists, then we're good. Okay, and that's not hard to prove. Okay, so yeah, that solves it. So I'm going to write it up. All right. So let AH intersect the circle ADE at point K. And then, whoops, sorry. And then since AB equals AD, so we have AB equals AD means that AH bisects angle BAD. And that means that K is the midpoint of arc PE. Of that circle. All right. And then let the perpendicular from K to DE meet AC at L. Okay, so L lies on the perpendicular bisector of DE, since and then we can also show it lies on the perpendicular bisector of AK by an angle face. And yeah, I didn't realize before that this just solves the problem, because so we have angle AKL is 90 minus angle KHJ. Actually, yeah, there's a whole bunch of ways to do this, but I'll do it like this. And that's equal to angle BD, the BDE, I think so. Let's see. And then
Yeah, BDE is equal to HBD because the figure is symmetric about TH.
BDE is equal to HBC by symmetry. So yeah, so BDE is equal to HBC. And that is equal to angle FBC, which is equal to angle LCA, L or LAK. So yeah, yeah. So we don't even really need this circle right here, although it does exist. So that means LA equals LK. So L lies on the perpendicular bisector of AK. So that means L is the center of that circle, and we're pretty much done. AEKD is the circle. Right, so now I will move on to the next one. Let's see, one more comment I see. Yeah, today is pretty fun. I kind of like this journal. Let's see. How do I go to the next one? Ah, sorry. Here we go. Okay, so we have the circle omega is inscribed in an isosceles triangle. C is the vertex. So I'll call this C. And I will call this point A. On the extension of AB beyond A and B. Okay, so let me hide the circle. Whoops. And okay, so AK is equal to BL. So I feel like I kind of want to use my compass tool here. So this is K. And then, yeah, there's a couple ways I could do this actually. I'm gonna do it this way. So if I reflect K about D, I want this to be point L. And the lines, whoops. Oh, because I already defined a D. Yeah, no, I want to call this, I'll call this M. And I want to draw the in circle. And I'll let I be the in center. And D is this point. So KD and LD intersect the circle again at G and H. That's kind of interesting. KD does not pass through I, so I'm going to want to make it not look that way. Yeah. There we go.
I guess we can.
Oh, sorry. So KD intersects it at G and LD intersects it at H. Okay. We want to show A lies on GH. So I'm going to hide all this extra stuff. Let's see. So we want to show GH, AC intersect the circle. Okay. So we want to show G, H, E, and M are harmonic. Yeah. So we want to show that's a harmonic quadrilateral. Is there something we can? Oh, I'm sorry, go on.
What do we want to show harmonic here?
Oh, I think he kind of just solved the problem. So yeah, this is an easy one, but basically if we can show EGHM is harmonic, then that would mean that the tangents at E and M and the line GH are concurrent at A, which is what we want to show. So we want to show HEGM is a harmonic quadrilateral, and I think we can do that by projecting through D. Yeah, that solves it. Okay, this is a fast one. Yep, well, all right, so so what, yeah, projecting, so we have M is the midpoint of KL. That means that KL, M, and the point at infinity are in harmonic conjugation. And then we can project those through point D. So and then we get H, we get G, D, M, E is equal to -1. And that's since DE is parallel to KL by symmetry. And so
GHM.
GHME. And then so GEHM is a harmonic quadrilateral. So and so that means that the tangents to omega E and M. So I'll write it like this. Concur. So that means that GH passes through A, or A lies on GH. All right, so we use stuff about harmonic quadrilaterals, and that solves it super fast. So yeah, 2 minutes after drawn. All right.